thank you all for showing up here today. This is our third What Physicists Do of the semester. It's my pleasure to introduce Dr. Austin Roorda from UC Berkeley. He's a professor of vision science and optometry from UC Berkeley. He works at the intersection of two exciting fields, one near and dear to my heart. They're both near and dear to my heart, but one that I actually practice in, and that is adaptive optics. I've known Austin for many years now. It's probably 15 years or something, working at a cross-disciplinary center, a Center for Adaptive Optics, funded by the National Science Foundation, and we were just kind of reminiscing about it. In the other part of his field, unlike my work on astronomical adaptive optics, he does adaptive optics looking at the living human eye. So it's very exciting work. This vision science includes the study of imperfections in the human visual system and fundamental research that he conducts into how vision works, including color vision, which was my first introduction to this, and I'm assuming you'll show something on the color vision, which I think is just an amazing result. And then how our eyes and their micro accommodations still allow us to see things at the limit of our resolution of our eye, and how to monitor eye disease and drug treatment therapies. His bachelor's of science in physics and his PhD in physics are from University of Waterloo. His PhD was joint with vision science or optometry at the time. He went off to the University of Rochester for a postdoc, then to University of Houston. I think that's where I met you, at that time, and then came to the North Bay area, as we all appreciate. He went to Berkeley. He's the recipient of the Glenn Fry Award, the highest research honor from the American Academy of Optometry. And if I may make a small joke, that I did not know that a founding member of the Eagles sponsored a fundamental award in research, the Glenn Fry Award. No, nobody, let's stop your laughter. Okay, so with that, I am very excited about today's talk about an intersection between physics, adaptive optics, and the human eye. Let's welcome Dr. Austin Roorda.
All right, thank you. So yeah, it's a thrill to be here. It's a thrill to see Scott again, and I love talking to audiences like this because I remember myself as a physicist, an undergrad physicist, thinking, what do I want to do? And this is a series, what do physicists do? And that's exactly the question I was asking myself. And in my fourth year of my undergraduate degree, I decided, okay, optics, that's one checkbox. I just really like optics. I like the cleanness of it. And then I wanted to do something health related. And that naturally drew me to the School of Optometry at the same school in Waterloo. And so that's where I did my PhD. And from that point on, from that fourth year project, which is equivalent to your capstone projects, from that point on, I was hooked. And I've been kind of doing the same thing ever since. And it's been a long path, and I never get tired of it. So I'm happy to talk to you about it. And feel free to interrupt. You can raise your hand, or you can yell if you're not that shy. And ask questions during the talk. It helps me gauge how well I'm getting through. And if I feel like we're getting distracted by a conversation about this or that, then I may shut you off and we'll move on. I have only about 40 slides, and we have about an hour, so we can go at a decent pace. So as Scott said, our tool is adaptive optics. There's a lot more tools than that, but the really sexy tool that we use is adaptive optics. It's still got some cachet to it. It's a lot of fun, and it kind of distinguishes our lab in this field of vision science. My lab and several others is becoming more popular, but I had the good fortune of being in at the very early stages, which I'll describe as I go through. But let me start my talk by giving you some scientific motivation behind why it is we do what we do. So this is two images, one a video and the other is an image. It's an image of the human cone photoreceptor mosaic. So cone photoreceptors are those photoreceptors that are sensitive during photopic conditions or daylight conditions. They come in 3 flavors, sensitive to bluish, greenish, and reddish light. And we compare the signals between the light capture of these 3 cell types. And so despite the fact that we only have 3 different types of photoreceptor, our human visual system can sense and distinguish about 10 million different colors in the environment. So how is it that we do that? And at the same time, the same detector that senses color has to sense space. So it has a dual role of detecting the color in the environment and to give you a sense of space, like reading text, recognizing faces, etc. And when we started taking videos of the retina on this fine scale, and what you see are the small dots are light reflected from individual cones. These are dots that represent the specific cone subtype. But what we learned, this has always been known, but it really made itself very clear, is that whenever we do fine spatial tasks like reading the smallest letter on an acuity chart, our eye is constantly in motion, as you can see. And so the motion that the eye undergoes over the time it takes to tell your optometrist what the letter is on that chart, the motion is many times the smallest resolvable element in the letter that you're trying to determine. We have no sense of that motion. We can sense tiny amounts of motion, but we don't have a sense of the motion of that image on our retina caused by our own fixational eye. And so you look at this, and it raises a lot of questions, and it actually inspired me to follow this field, to try to understand this. So the question is, how does the cone mosaic fulfill its dual role of enabling spatial and color vision? We're not the only ones in the world that ask this question. In fact, many people in vision science have questions just like this, and there's many different approaches. And so this is an example of some approaches. I think it's just enough volume you can hear the activity there. But one of the ways you can learn about activity or how the retina works is you can take tissue from an animal that has been sacrificed, look at it under a microscope, excite it with light, record with electrodes, record the activity. So they do retinal physiology under a microscope. So that's one approach to try to understand how the retina works. Another approach is you get animals that have maybe been conditioned in some way. This is a monkey that Jay Knights at the University of Washington gave genetic therapy to give that mouse color vision. And he's trying to understand the processes behind color vision. And so he can do the treatment in a monkey and have the monkey do psychophysics or subjective tests to see how sensitive they are to color. Another way is you could use an optical system to stimulate the retina while recording activity in the neurons in the brain. So you can look at the connections between cells and neurons in the retina and neurons in the brain to try to elucidate or learn about the circuits that underlie spatial and color vision. And then a final approach is to do what's called psychophysics, but it's just try to infer properties, basic properties of the circuits that underlie vision by doing subjective tests. So for example, if I want to learn about your color vision, properties of your color vision, or any mutation that causes your cone mosaic that failed to form normally, I could do a color vision test like this. This is not that unfamiliar to you. This is even less unfamiliar. If I wanted to learn about optical and or retinal limits to vision, I might be able to deduce that by having you read letters on a letter chart. Okay? So there's many different approaches. Many different scientists take different approaches to tackle the questions that we have. What we want to do with adaptive optics is try to bridge 2 of these fields. We want to be able to work at the cellular level, be able to stimulate and even record from individual cells in the retina, and do it in living humans where we can match that precision, that cellular level access, with subjective tests in living humans. So how is it what are the challenges that we have? Okay, so this is mostly physics students, right? And you may have taken some optics. There's a basic property of any optical system that tells you that as the cone of light gets steeper, the cone of focusing light gets steeper, or as the numerical aperture of your optical system gets higher, or as the pupil that's focusing the light gets larger, they're all doing the same thing, increasing the cone of that focused light. As that cone of light gets steeper, the focusing ability of an optical system improves. And this shows on a relative scale the size of the focused spot. It's an airy disk because the eye is perfect or diffraction limited, but it shows the size of the focus spot for a physiological range of pupil sizes in the eye from 1 to 7 millimeters. And you can see that the capacity of the optical system to focus light to a small spot improves as the pupil size gets larger. And in fact, through a 7 millimeter pupil, which is a numerical aperture of 0.2 for those microscopists in the audience, the focus spot is on the order of microns, about 2 microns, which is about the size of a cell. So the human optical system has a capacity to focus light down to spots as small as a single cell, provided that you use reasonably large pupil sizes. So, okay, knowing this, just armed with this information, you might decide as a physicist to build an optical system. And if I want to take an image of the inside of the retina of a human eye or focus light to a single cell in a human eye, I'm going to build a system that uses the largest pupil I can to take advantage of this increase in numerical aperture and the improved focusing ability. Okay, so you do that, and you set the system up, you try to take an image, and it fails miserably. And the reason it fails miserably is because the eye is not perfect. It's not even close to perfect. It's terrible. So rather than the focus spot getting smaller as the pupil size gets larger, when you get to larger pupils, you start to face irregularities in the shape of the surfaces, the cornea and the lens, misalignments and tilts, relative tilts between those components, which all conspire to, rather than make the image sharp, they make the image blurry. So you're trapped on two ends. Diffraction gives you a large blob for a small pupil, and aberrations gives you a large blob for a large pupil. And it's not that surprising then that the human visual system during photopic conditions does not have a pupil size like this. It doesn't go as tiny as this. It actually hovers around 2 to 4. It turns out that 2 to 4 millimeters is about the optimal pupil size for a human eye for the best spatial, the sharpest focused vision. But while that's okay for vision, and there's arguments why you might not even want a sharp focused spot like this for vision. This is okay for vision, but it's not great if you're an eye doctor trying to look at the retina of your patient, or if you're a scientist like me trying to understand or probe activity or function on a cellular level in the patient. So we want to harness all the focusing ability of the eye, and so in order to do that, we need to correct for the imperfections that give rise to this and get to this, and that's adaptive optics. That's what adaptive optics allows us to do. Same reason adaptive optics allows you to take advantage of the focusing ability of these massive telescopes. We need to take advantage of the focusing ability of a pupil size as small as 7 millimeters. I'm not going to go over the basics of adaptive optics, except that it involves 2 stages, 2 parts. First, you have to carefully measure what the imperfections of the eye are. And the best systems to measure the optical imperfections of the eye are Shack-Hartman wavefront sensors, the same type of sensor that's most commonly used in astronomy. That was first used in the human eye around 1990. So we can measure exactly what the imperfections are. Then we build an optical system. I'll go over some of the optical layout of that system. But we build an optical system where in the path we have another optic that has an equal and opposite aberration to what the eye has. So upon hitting each other, the aberrated beam coming out of the eye, its aberrations get canceled by the aberrations of the mirror. So you render the wavefront flat or render all the rays parallel so they focus to a nice small spot. So you make the wave, this is a map of the distortions or the imperfections in the eye made flat with adaptive optics, and you can go from a point spread function like this to this. So the information is not lost by the aberrations, it's just mixed up. And adaptive optics, you just got to unmix that information. You need to know what the mix-up is, what the aberrations are, correct for them, and you can regain that focusing ability. This, of course, is nothing new to people in astronomy, and this is just a nice example of the kind of benefit that astronomers get if you have your telescope on the ground looking through the turbulent atmosphere. the star is not sharp because of the phase distortions or imperfections, in a sense, or distortions in the wave as it passes through the atmosphere of the Earth. And you can measure and compensate for those, and if you do that in a telescope, you can render a very sharp, focused spot. This is from Claire Max at UC Santa Cruz. This is the focus spot. Of course, when you apply adaptive optics then to look at an extended object, like a galaxy, this is what you would see without AO, and this is what you would see with AO, so you get much richer, higher resolution information in the image. And that's for distant galaxies. And this is probably not the latest version anymore of an image of a planet, but in 2008 they used an adaptive optics system to actually see planets orbiting stars within our own solar system, within our own galaxy. Sorry. I'm not an astronomer, so I'll probably say some dumb things. Forgive me. But okay, so how do we apply it to the eye? That's what we're going to focus on today. First of all, we need to measure what the imperfections of the eye are. And the retina is not its own source of light. So I need to put light in to form what we call what astronomers would call a laser guide star. So you form an artificial light beacon on the retina. So we do that with a laser beacon. It shines and focuses to a reasonably small spot. It doesn't have to be super tiny, small spot on the retina. That light will scatter off from the retina in all directions and emerge from the eye. Here, that's the red beam here. We pass it through a couple of telescope systems. So we image the pupil of the eye onto the deformable mirror, and then we image the pupil of the eye onto the wavefront sensor. Initially, this mirror would be flat. And so in this configuration, the wavefront sensor would be measuring what the optical imperfections of the eye are. Then we use what's called a closed loop optical system. All of this would be familiar to any of those in astronomy, astronomical adaptive optics. We use a closed loop system whereby the information from the wavefront sensor is used to drive the mirror, and then the mirror can see how well it's done. So the mirror continues to shape this mirror to compensate for the imperfections that it's seeing, and when it's satisfied that it's rendered a distorted wavefront flat, in other words, when it sees a flat wavefront, that means it's ready to go. Then you use a regular camera where you use a flash lamp. In this particular configuration, you use a flash lamp to illuminate a spot on the retina, and you have a camera that looks at the retina through the deformable mirror. Okay? So you can illuminate the retina and take a picture of it with a CCD camera through the deformable mirror. So it's a pretty simple optical setup. The complications are writing a good control loop, getting a good high signals and noise measure of the wave aberrations. But a Shack-Hartman sensor is very useful for this. And we learned a tremendous amount from the astronomers who had been in the business for a long time before we had gotten in. We learned a tremendous amount from them about how to write good control loops to have the information from the wavefront sensor properly drive the mirror. So when you do that, this is kind of benefit. So you can measure the more lines you see on the wave aberration plot, the more aberrations, the larger the point spread. This just shows adaptive optics in action. So we can do it reasonably well now. We've had lots of years of experience, benefited a lot from astronomers, as I said. And somehow I'm missing, oh no, okay. I'm not missing a slide. So this is the University of Rochester, David Williams lab. This is David Williams here, along with a postdoc and a graduate student, Don Miller and Jinsung Liang. So it's really just the three of them working on this system, and they built the very first adaptive optics fundus camera, implementing the method that I had just described in the previous slide. So David is the subject. In the optical path of light coming from his eye, we have the deformable mirror, we have the wavefront sensor, and we have the retinal imaging camera, and we have a flash lamp that illuminates a patch of light on the retina. This is what you get. I was the luckiest postdoc in the world. I showed up within months after they had completed the system, so I got to use it to do everything I did was generate a lot of excitement. I took way more credit than I should have for the work. These guys deserve most of the credit. I just got to use it. This is the benefit that you get. And so without adaptive optics, you have a well-corrected eye. an eye with relatively low amounts of imperfections. And then you carefully correct what you can correct, which is defocus and astigmatism in the eye, the same thing that your spectacles correct. Those, by far, are the aberrations that give rise to the blur that you would experience. And we can correct those using traditional methods. We had to back then. And if you do that, then you take a high magnification picture of the retina without adaptive optics, and you can see some structure in good cases. But when you turn on the adaptive optics, you can start to see what underlies that hint of structure here, and that is the entire cone mosaic. So each small spot is the light scattered from a single cone photoreceptor. The cones themselves are optical waveguides, which make them actually quite nice with reflective structures within them. Makes them quite nice retroreflectors in a way. And so they're, as long as you have the resolution, they give enough reflection that they're fairly easy to see. And in this case, you can see virtually every cone across the mosaic. You can even see the dim one and one that is apparently missing. The dark line is a shadow cast by a blood vessel that's running in front of the photoreceptor mosaic. This image is about 150 microns across, so 0.15 millimeters. The vessel is probably almost as far in front of this photoreceptor layer as the image is wide. So what this shows is not just a sharpening of the image, but it's really a paradigm shift in how one could use an ophthalmoscope to study vision, because it takes ophthalmoscopy from a tool that can look at the gross features in the retina, and optometrists and ophthalmologists have been using this for decades. They can see leakage in blood vessels, changes in pallor caused by sick neurons and cells. It's taken it from that level of diagnosis or study to that which would be achieved only in a microscope, a single cell level. So that's where it's a paradigm shift, because if I want to study vision or study the health of a diseased eye, I can now start looking at it in living eyes on a cellular scale. So that's where all the excitement was generated, because it turns out to be a microscope for a living human eye. So I'm going to move forward. We got a lot of mileage out of the system at the University of Rochester, but when I moved to Houston in 1998, I was motivated to integrate adaptive optics into a slightly different type of imaging system. So what I had shown you before and what was built at the University of Rochester was what's called a flood illumination camera, or basically just a CCD camera that looks at the retina through the adaptive optics system. Okay, so it just takes a snapshot of the entire field of the retina. For lots of reasons, we wanted to integrate it into a different type of imaging modality, and it's a scanning laser ophthalmoscope, which is just like a scanning laser microscope. It does not take a full field image in a single snapshot. It generates an image over time by looking at the scattered light from a focus spot as it scans across the retina. So it builds an image pixel by pixel. It does it very quickly, so we have scanners that go to about 16 kilohertz, so we can record video this way at about 30 hertz. This is the system. It's decidedly homemade looking. We design them and build them. You still can't really buy a system like this. They're not commercially available, although companies are starting to develop them. But this is an example of one of the ones that we built in our lab. So I'm going to give you a series of 4 slides that show the progression since that time, which is around 2002, to the current day, where we've got a fully developed system for not just imaging the retina, but measuring structure and function of the retina. So this shows the adaptive optics in action. We're recording a live image now. When you turn the adaptive optics on, the image gets brighter. It gets brighter because it's a confocal imaging system. How many of you are familiar with confocal microscopy? So confocal microscopy is a way of axially sectioning through depth. It only accepts light from the plane of focus. The sharper you make that light at the plane of focus, the more light you get through your confocal pinhole. So the image gets brighter. It gets sharper because of the point spread function gets narrower, as I'd shown before, and it gets more contrast as a result of the narrowness of the optical section. So that's adaptive optics, and that's what we were doing as early as 2002 in our scanning laser ophthalmoscope. Yeah?
I feel like I'm seeing motion in the, I mean, you talk about these being blood vessels. I don't know if that's moire or if that's actual.
No, that's real. So the capillaries are sitting in front, And what you're seeing are shadows cast by red and white blood cells as they're coursing through. And there's a whole other application of adaptive optics imaging where people, including people in my lab, have used it to measure the microvasculature. Yeah, sorry, I forgot to point that out. I've seen this enough that I forget that it's even there. Okay, so why do we want to use a scanning laser ophthalmoscope instead of a regular camera? Well, one of the features that a scanning laser system has that's unique is that not only can I scan a focus spot to image the retina, but just like the way you put an image on the phosphor screen of an old-fashioned television set, you modulate the power of the red, green, and blue guns as they're scanning across the screen. We can modulate the laser while it's scanning across the retina to put a picture directly onto the patient's retina. So if you were normally being imaged, what you would see would be a red square comprising the extent of the raster scan on your retina. If I modulate the laser at the appropriate time points while I'm scanning, then I could put a picture directly onto the patient's retina. And the patient would see it. They would see a black E within a red square. Now, if that same laser was turned off, if it was the same laser that was doing the imaging that I turned off to project the image onto the retina, then that pixel at that point in time would not record any light. So the stimulus that I delivered to the patient's retina that they saw would be encoded directly into the video that I record. So this is not an overlay of an E onto a video. It's the actual video that I record. So you can imagine now, appreciate the strength of this method, this technology, because now I can administer a vision test for my patient. I might ask them to do an acuity test. What letter do you see? Or how much light have I put on? How much light does it take for you to sense the flash? So I can deliver that just by modulating the laser that I'm scanning with. But then with the record, I can see exactly how that patient, that subject is interacting with the letter on a cellular scale. So when they're deciding what the letter is, I can know after the fact exactly which cones have interacted with that letter and exactly how has the eye moved over the time it took for them to make that decision. So it allows me to do subjective vision testing, but then relate it to the function of the structure of the eye on a cellular scale. You can see that what I'd shown you before is the eye is constantly in motion. And so I can know exactly what cells have interacted with whatever light I put on the retina. But what I'm unable to show, at least in this video, or what I've been unable to do, is to target an individual cell. And I might want to probe this cell, right? And say exactly how sensitive is this cell to the light. So I want to target individual cells. So there's a couple of steps involved in that. First, we need to stabilize the retina. So we're recording a video, but we had excellent programmers that we've worked with, mainly from Montana State University, that worked to be able to stabilize those videos in real time while they're being recorded. So we have systems where you can see the eye with all its normal motion, but you can see right beside it a frame which has the eye perfectly stabilized. So now the cell is locked in place when I've stabilized the video. Of course, the byproduct of stabilizing a video is recording the eye motion, right? We get both of those things. So we get a really exquisite eye motion trace. Actually, we can trace the motion of the eye extremely quickly. We're not limited by the frame rate of the scanning laser ophthalmoscope. And we can do it on the scale of a single cell. So it turned out to be the world's most accurate eye tracker as well. But what we were really interested in was stabilizing the retina in this manner so that we could deliver a stimulus to a targeted location. So now I can take...
What's the difference between the purple and the blue curves?
Oh, vertical and horizontal. Sorry, yes. So now I can take the eye motion information in both X and Y and control the delivery of the stimulus. I'm not actually physically moving a mirror. I'm just controlling the timing of when I turn the laser on and off so that it remains locked on target. Again, this is not an overlay of the letter. In fact, if it was an overlay, I would have made it a lot more stable. But you can see that I'm doing the best I can to get an image directly onto the targeted location. And if you look at it, there's still a little bit of wiggle left in the stimulus and its ability to lock onto those cells. That little wiggle, though, is on the scale of a cone. Its standard deviation is a fraction of the size of a cone. Yeah.
Are you monitoring one eye at a time?
Only ever doing one eye at a time.
And do you have to use some kind of technique for determining the stimuli frequency, like it gives you like green light versus red light, you use your normal eye, you just use red light?
Oh, I'll talk about different colors of light in a moment. Right now, all I'm doing is turning the laser off to stimulate, so the patient will see a dark E on a red background. But I'll mention how we can integrate other wavelengths in. Okay, so we'll get to that. Anyway, the point is that we can now we can keep a stimulus locked on target. Okay. Okay, here we go. Okay, so you must have seen my next slide, because we're right here. So how do we use this now? I don't just want to put black spots on a red background. In fact, what I want to image with is a wavelength that's minimally visible. So we use infrared, near infrared, 840 nanometer. It still appears red to the patient. We want to work on that to try to make it completely invisible. But at the moment, we're using reddish appearing light to image. But then I can hook up any other laser into the system. And instead of turning this laser off at a certain time point to put a black spot on a normally red background, I can turn on a green laser and make it flash at the targeted location. It's not as easy, though, as just simply aligning another laser into the path. The eye has a huge amount of longitudinal chromatic aberration. Difference in focus position is a function of wavelength. And transverse chromatic aberration. The longitudinal chromatic aberration is predictable in the population to within a fairly small amount. But the transverse chromatic aberration is not. And so it took us a lot of effort to correct for that, to measure and correct for that. But we can now do it reasonably well. So I could be imaging the retina with infrared and then deliver a green stimulus to any targeted location. Of course, the green stimulus is not going to naturally show up in the image. But this white cross, this blinking white cross indicates where it lands. So the best proof that we're indeed doing what I think we're doing, which is delivering a small, visible green light flash, in this case, to the targeted cone, was in this paper published just last year. And in this paper, we imaged with infrared light, and then we would deliver green light to the targeted cone, correcting for the transverse chromatic aberration and the longitudinal chromatic aberration. And if indeed we're doing what we want to do, then you should be able to see a change in sensitivity if you move the light from on the cone to some space between a pair of cones. You should be able to see a drop in sensitivity. If you're not doing it right, you might not see that drop. So this is two tested conditions just illustrated on this slide, where we place the beam of light onto the cone and we place the spot of light off the cone. And this shows two plots of the sensitivity. It's actually the threshold. The threshold tells you how much light does it take for the subject to see a brief flash. So when you have a higher threshold, that means you need more light than if you have a lower threshold. So when you place the spot in the gap, you need more light for the subject to see it than if you place the spot onto the cone. And this just shows a procedure whereby we do multiple trials. We keep peppering the same cone, changing the amount of light until they see it 50% of the time. So it's a classic approach to measuring the sensitivity threshold that vision scientists have been using for years.
I have two, if I can be brief.
Sure.
One is, this was probably fundamentally unknown, like what is the sensitivity of various parts on the eye. I mean, I want to stress this for the group to say that, going in and doing this live in the human eye, this would be the first mapping of how sensitive a person is at various parts of their eye.
Yeah.
The second part was, I'm interested, did you choose green specifically? Does it fire on all of the cones? There's quite a breadth to the wavelength response to the three cones, the red, green, and blue. And so I was just wondering, do you get a measurement of like, oh, we picked a green cone because they're a little easier with it, or is it broad enough that that the patient, if you're tickling one of the red cones, the ones that's more sensitive to red light, you're still seeing it because
Right.
these distributions are broad.
I'll show you that the three types of cones are broadly sensitive. And so the red, in fact, we don't even call them red, green, and blue because they're misnomers. The red sensitive cone, we'll call it the long wavelength sensitive cone, peaks at about 563, which is not red. It's not even orange. It's not even yellow. It's on the green side of yellow. Okay. The greenish sensitive cone peaks at about 535, which is decidedly greenish. The common sensitivity to both, or the wavelength to which they're both sensitive, is about 5. What did we use? 543. It's around 545 nanometers. The blue sensitive cone, or the short wavelength sensitive cone, is way off to the left. And it peaks in sensitivity around 440 nanometer. So we're probing sensitivity here of either the middle or the long wavelength sensitive cones. That's why we chose 543. But we've done other experiments, not all of which I'll be able to describe today, where we were trying to map the cone mosaic by measuring sensitivity of an individual cone to different wavelengths. And I'll mention some of that as I move forward. So anyway, this was proof to us. It just represents the technical achievement of focusing the light to a small spot to a targeted location. And if, for example, the spot was not as focused as we thought it would be, it's hard to know exactly in your adaptive optic system whether you've corrected everything properly. So if it were not as focused as you wanted it to be, you wouldn't see any change in the threshold because the spot wouldn't be this small. It would always hit 6 or 7 cones no matter where it was. And if we didn't correct the transverse chromatic aberration the way we wanted to, then you might see granulation and sensitivity at different locations, but it wouldn't be at the place where we thought it was. So I might think I was hitting here, but maybe I was hitting a gap. And so I'd see a reduced sensitivity. So this was a pretty good assurance to us that indeed we were doing what we thought we were doing. So I'm going to focus on 2 application areas, color vision and spatial vision. And we'll start with color vision. And this is kind of where I got started as a postdoc, because one of the first things I did at the University of Rochester was I got to use that wonderful device that Junjong Liang and Don Miller and Dave Williams built. And I used it to measure the distribution of the cone types in the retina, the 3 cone types, long, middle, and short wavelength cone types. And in fact, until just this year, the only system in the world that had ever done that was that one in Rochester. And other people have tried, and then other people got distracted by doing other things like medical applications and different studies. But anyway, we needed to recapitulate that ability to do it. And so my postdoc, Ram Sabason, did it in my lab, and so we're able to redo what we had done way back in 1998, map the 3 classes of cone. Okay, why did we want to do that again? That's not a high-impact paper. It's published years ago. The reason we want to do it is because now we can ask the big question. The big question is, this is the cone types. But every vision scientist wants to know, what do they see? What do you see when you stimulate individual cones? And how is color vision? How does this mosaic fulfill its role to give us the exquisite color vision that we have? So here's what we're going to do. We're going to image the retina with infrared light. We're going to track the retina. And then at targeted locations, targeted cones in the mosaic, we're going to flash a green light. 543 nanometer, equally sensitive to both the long and middle wavelength sensitive cone. Okay? And we don't know what color they're going to see. A cone on its own does not sense color. The cone only measures the amount of excitation. And so it does not know the wavelength that's hitting it. It just knows how much is excited by that light. So what is a subject going to see when you flash light into an individual cone? And how does it relate to the cone subtype? So we flash light. I'm showing it green because that's the color of the actual light source. We flash light, and we go in with an open mind as to what they're going to see. So we give them a tablet view. We kind of narrowed the choices to red, green, yellow, blue, achromatic, like white, gray, or not seen at all. So ideally, this would be the environment under which we would do the test. So you'd be the subject and you would see nothing. You would not be aware that I was tracking your retina and targeting individual cones. And you would see a flash, and then all you have to do is say what color it was. We can't really do it because the 840 nanometer light is sort of visible, so we have a reddish background. And context means everything in color vision. So we have to be aware of that. Plus, when we're trying to deliver the green light, we try to turn on the green light at that appropriate location to target that cone. We do it with what's called an acousto-optic modulator. And when an acousto-optic modulator is off, it's not really off. There's always a little bit of green light leaking through the background. And so you might have a flash here, but the cost of getting a tiny flash at that location is a little bit of green background. So, okay, well, now we have a greenish, reddish background. So we have to live with it, so we just add another one. We just have them look at a DLP projector through a beam splitter. So we add it all together so we make it gray or white, achromatic. Okay? So you have to be very careful about those conditions because that means everything. That's a huge factor in governing color vision. But now they're doing it in a white background. So it's a fair enough test to ask what color would you see if you overstimulated a single cone against the dim white background. Okay, so this is the cone mosaic. This is the experiment. So we target a cone. We know the cone mosaic. We can go back to these cones day in and day out. My grad students and postdocs are champions. They have nicknames for the cones. They've got the mosaics memorized. They just go back to the same cell day after day, and it's a very time-consuming process, as you might appreciate. Anyway, we go to a single cone, flashlight. What do they see? Hit another cone, flashlight. What do you see? What do you see? What do you see? What do you see? So what we do is we pseudo-randomly address. We don't tell the subject what cone we're hitting. They don't know. We choose a bunch of target cones, pseudo-randomly address them so they don't know what order they're being stimulated in. And we stimulate them each 20 times. So we get 20 responses, color responses per cone. When we do it, we have an unambiguous record of where the stimulus has landed on each trial. So this just represents 20 stimulations of 3 targeted cones. And they're clustered pretty tightly, so we're hitting the target reasonably well every time. Occasionally one gets off into space, but we can just throw out the responses from those trials. So we get very clean subjective testing from that cone exactly. Of course, each cone, this indicates the location, but each cone records a color or elicits a percept of a color. And in this case, when you stimulated this cone, it saw green or white most of the time. This one saw red or orange most of the time. And this one never saw anything but a white flash. Okay? So we do this for all the cones in the mosaic. So you can just see we have very careful control over our data. Now, what we discover is, first of all, the light is green, 543. Yes?
So you're doing each cone 20 times. Do they say 20 times what they saw, or does it average over?
No. Yeah, so every trial is, they have to report what they saw. Yes. And the stimulation is it's about, I think it's about 300 milliseconds. Oh, sure, yeah. It's not nearly enough light to bleach the cone or adapt the cone. So we could hit this as many times as we want and still get similar types of responses. So we use light that is just maybe 4 or 5 times above the threshold of them being able to see it. So it's a dim flash. Oh, sure, yeah. All the reporting is the color, but the spatial properties of the stimulus are something that we don't record, but we're very interested in. Because exactly. In fact, that's one of the ways we might want to map the receptive fields. Now, we're at a location close to the fovea, and close to the fovea, the receptive fields that mediate color vision are thought to be single cell center. So they're not pooling information. So those are good questions. I apologize if I'm confusing people in the audience, but receptive field, the receptive field is the, well, okay, there's 120 million photoreceptors in the retina. And there's only 1 million. That sounded like a lot 25 years ago, 1 million, but a mere megapixel of information conveying light from the retina, from the eyeball to the brain. 1 million axons from the ganglion cells, which pool the information from the cones, conveying the information from the eyeball to the brain. So the reduction is 120 to 1. But at the fovea, which is that part of the retina that's designed for spatial vision, for fine spatial and color vision, you have at least 2 lines per foveal cone near the fovea. So there's actually a convergence at the fovea, which means even a more massive, there's a divergence at the fovea, which means even a more massive convergence. Not like a normal camera, not like binning pixels on a CCD camera. It's very heterogeneous in terms of what kind of processing it does across its surface. We're very interested in how those receptive fields are, because it's not actually really well understood how they're constructed. A receptive field would be those cones that comprise a single line connecting the eyeball to the brain. And that would form a collection of cones, which would be the receptive field. Okay, so these are the color responses. The light is green, but the responses are decidedly not green in many cases. Very pure as well. So this cone, every time it was stimulated, the subject did not know which cone was stimulated at any given time, but they thought they saw red. And the results are very pure, we call them. Incorrect, as you might expect. Why should we think they should sense the color when you stimulate an individual cone? But very pure, nevertheless. So Ram invented this little tool, this plotting method, to plot the histogram of the responses in the form of an annulus. And the reason we do it as an annulus will become clear here. So this is all the data. And it's just data. It's overwhelming how much information is in here. But what you see is the cone types that we measured and the responses that we're getting from the color responses that we're getting from the cone types, the percepts that were elicited. And what you find is that cones that are sensitive to the green part of the spectrum, or these cones, the middle wavelength sensitive cones, predominantly report greenish responses or achromatic responses. Cones that are sensitive to the longer wavelengths report reddish or achromatic responses. The short wavelength sensitive cones, in fact, this is our control, but they report fewer events of seeing. And this actually shows how much light might be leaking into the neighboring cones. But this is, I'm not going to dwell too much on the interpretation of this, but there are different models for how the retinal wiring might subserve color vision. And a lot of the wiring in the form of the composition of the receptive field. How the cells, the photoreceptor cells, are connected to the ganglion cells whose axons project to the brain. We want to know what those circuits are. And despite lots of effort by many people over many years, it's not really fully understood. But it is believed that some of the lines that carry information, the lines that carry information from the retina to the brain, carry color information in some form, carry difference information that may estimate the magnitude of the difference in the signal between adjacent cones. Yeah?
So, yeah, I've already explained this, but the different types of cones, the blue, green, red, those don't have anything to do with the color that cone sees.
Well, they do in the sense that when you stimulate this cone, it will see red, even though the light is green. So they have a lot to do with the color, and there's very few instances where a cone, like a reddish sensitive cone when stimulated, would report green. But this is all new information. Nobody has ever known or been able to predict, known what the percepts would be when you stimulate individual cones. So we're sitting on a lot of information to process. And
Austin.
Yeah.
May I follow up? The coloring on the background image
Yeah.
is from earlier studies saying which type of cone those are and which sensitivity. That is not a true color
That's
image
right.
of the back of the human eye.
That's
I just wanted to follow up that that's a mapping, and now they're putting on
That's
on
right.
top
Yeah.
of the mapping a measurement of saying, what if I hit it with green light? What does that cell see?
And the middle part is what kind of cone it
Yeah.
was.
This is the type of cone. This tells you what kind of.
It tells you what percentage of
Yeah.
your eye you've got to see of the different colors.
That's right. So right. So it tells you. It tells you. In fact, if you wanted to reverse engineer your color CCD camera, you might stimulate a single pixel because pixels are sensitive to reddish, greenish, and bluish light. And you might stimulate a single pixel and then see, okay, well, how is the image rendered? And you could figure out from how the image is rendered what the circuit might be that underlies the calculation of color, right? And it's doing some sort of different signaling, but it doesn't. It's not just going to show a gray spot corresponding to how much that pixel excited. It's going to interpret that signal as being something having to do with color. So the retina is no different, except we didn't build the retina. But we have to reverse engineer it to try to understand what it is, how it works. It's our retina. We have to reverse engineer it nevertheless. And so, I won't go into detail because I'm going to run out of time. But one of the things that we're very interested in is clustering of the results. Why is there a whole bunch of achromatic responses here? And it turns out that a cone that senses the color of its subtype when it's more likely to sense a color when it's surrounded by cones of similar type. And that's giving us some hints as to what the wiring is. And so this is still work in progress. My postdoc is, and other collaborators are continuing to work on this. Now I want to change gears a little bit because I promised you something about color and something about spatial vision. And this was very cool. It's very new. We just submitted a paper on this, so fingers crossed that it'll go to review and get published. It'll get published somewhere. We're just going for high impact right now. So here's a question, and I'm going to take a poll of the audience here. So we can do a visual acuity test, and I can control the stimulus however I want. And I told you that when you're looking at the smallest letter on a letter chart in the optometrist office, over the time it's taken you to tell your optometrist what that letter is, your retina has moved a tremendous amount, or the image has moved a tremendous amount across your retina. So this shows the retina moving behind the stimulus. So I can do a visual acuity test this way, and I can do a visual acuity test this way, where rather than letting the letter move naturally behind the moving retina, I lock it on a location. Okay, so one of the things happens, I'm going to rule this out as being a factor that will govern the difference between these two. One of the things that happens when you stabilize an image on the retina is it, who knows?
Like floats around in the
No, well that's,
vision?
it may appear to move, but no, it will fade. An image that's stabilized on the retina for long enough will just fade from view completely. It'll disappear. If presented briefly enough, though, you can see it. But after about 3 seconds, it'll be completely gone, even though it's presented with very high contrast. But that's not the reason why. That would be a good reason why a stabilized image you would do very poorly on it, because you would be able to see it. But we present it briefly enough so you can see it. Okay, so who thinks you're going to do better under this condition? Put up your hand. And who thinks you're going to do better under this condition? Put up your hand. That's right. So it's fair enough. Of course, why would I, you're already kind of clued into this being an evolution of the visual system, or an adaptation of the visual system. But indeed, it's the case. So the majority wins here. Natural eye motion, object viewed under natural, where the image is allowed to move caused by natural fixational eye motion, you will see that letter correct a higher percentage of time than if it's stabilized. And in fact, the letters that we used were letters that were right at, even below the Nyquist sampling limit of the photoreceptors. And so it's surprising to me that we could process that information temporally on such a fine time scale as to be able to confer better acuity under this condition than this condition. So to end the talk, I just want to explore that dynamic property of vision a little bit. And so many of you will be familiar with sampling limits and Nyquist sampling limit. Well, you can think of the photoreceptor mosaic as a discrete array of pixels. Of course it's not, and I'm a big believer that it doesn't really behave that way, but let's think of it that way anyway to begin with. So this is an image of the foveal cone mosaic. The cones in the fovea the spacing is the smallest right at the very center of the fovea, and cones get bigger and further spaced as you move away. Another indication of the specialization of the fovea in the retina compared to other parts of the retina. So that they're maximally dense right at the center of fixation, and then they get bigger as you move away. And this just plots it on a color scale. It plots the Nyquist sampling limit. So what you can see at the very center of the fovea is about 60 cycles per degree, which would be about 20/10 letter. 20/10 letter is half the size of a 20/20 letter on an acuity chart in an optometrist's office. So the fovea has the capacity to see 20/10, at least if you think of it as a Nyquist sampler. And then you move away, and it actually holds on to that ability pretty well out to even moderate angles. 20/12. You have to be a few degrees away from fixation to have a Nyquist sampling limit of 20/20. Anyway, so I'm going to just do a toy model here of dynamic acuity. And I'm going to take a model of the foveal cone mosaic, and so they're smallest here, a little bigger here. And I'm going to calculate in a model what the information is that can be conveyed by the photoreceptors to the brain, the maximum information. So what I do is I lay a letter down on the retina, and then I look at each cone and calculate how much each of these cones is excited. So if the letter doesn't land on a cone, this one has nothing. This one just overlaps it a bit. It's got some excitation. So what is the excitation map caused when you put an image like that on the retina? Well, this would be it. It's a 20/10 letter, so it's half the size of a 20/20 letter, but it's sampleable by the foveal cone mosaic. So if I were to ask you what that letter was, and in our experiments, we usually are asking our patient to tell us what the orientation of a letter is, which way the bars are pointing. It's easier to do because they're trapped in an instrument and they can use a computer to record the responses. So anyway, you can see that reasonably well. Okay, so I'm going to look at these excitation maps and see how do they change when you change the letter size, how do they change when we add eye motion to the model. So I'm going to look at a 20/10 letter, and I'm going to just take a snapshot. So this would be equivalent to the kind of signal, the maximum signal you could get if the image were stabilized on the retina. Because you get no other looks at it. You're just stuck with that array of cells sensing that letter that's landed on the retina. So what orientation is the E? Are the bars pointing down, left, right, up, down, down? Okay. Most people will be able to see that as going down. So now I'm going to look at the same letter. Remember, we see it as being perceptually stable. The retina's moving behind it. We don't sense that motion. But now if I dynamically sample it, it looks a little better. You can tell it's down. And then the visual system is a little sluggish. So if you excite it with a photoreceptor with a brief flash, there's a little bit of time. So it integrates the signal over time. So if you add a little bit of integration, it's even better. Now you can see it. You can see it pretty well. So now I'm going to push it down a little further. So I guess what I'm representing here is that provided that our visual system, does our visual system have the capacity to integrate this information over time, to process temporally the changing image that's moving across the retina, to be able to do better than a stabilized condition. And our visual system can do it because you're already doing it yourself for me. It's not happening at your photoreceptor level, but the reason you're doing better on this, none of the representations, the individual representations, are any better than this. But you're able to synthesize and integrate that information over time to yield a more higher fidelity percept. So our visual system has this remarkable capacity to do that to begin with. And this just makes that clear. So now I got a 20/8 letter, so it's even smaller. It's 20% smaller than a 20/10 letter. Snapshot, which way do you think the letter's pointing? Up. Okay, that's pretty good agreement. I think that pretty well confirms it, and if you integrate it, it's even a little better. But it's getting a little tough, right? And if I go to an even smaller letter, it gets even tougher. Which way do you think it's pointing? Okay, now I get some mixed responses. This doesn't help a tremendous amount. This doesn't help a tremendous amount. But so what is the limit, though, to our ability to process this information? Yeah, maybe down is right. What is the limit to this model? Is it the Nyquist sampling limit or the photoreceptor mosaic? The letter is already smaller than the Nyquist limit. This one was as well, by the way. This
one big cell in the middle there.
Well, here's how you can improve on this. So we can potentially see 20 over 7. All I have to do is make the aperture of the cone, the sensitivity aperture of the cone, narrower. So the cone, I model the sensitivity of a cone as being some kind of Gaussian across its full aperture. But if I pinch it down a little bit, it makes it more sensitive to a moving edge. It's going to not change, but then as soon as it gets to the center of the cone, it's going to abruptly change. So if I make a smaller aperture, actually you can do pretty well. And if I integrate it, you can easily see that it's pointing down. And this is 30% lower than the Nyquist sampling limit of the cone. In fact, you can push this to the limit where you don't even need a complete mosaic of cones. In the limit, if you just had one cone with a very, very narrow aperture, if you could integrate it long enough, you could reconstruct the image on the retina perfectly. And I'm a strong believer that our visual system does this. And the proof is that you're already able to do it with this kind of information.
So isn't that what the rods do?
Yeah, except the rods are not wired. So this is where the receptive fields come in. The rod signals are pooled. There's never a one-to-one connection between the rod and the brain. There's always binning going on between the rods. So they're not small for any functional reason. And they don't subserve fine spatial vision. So if you ever tested,
They see movement.
they can see movement, but they don't integrate movement in a way to yield fine spatial vision. So we can do rod tests, and that would just prove that they're not going to see very clearly. So they're small for other reasons. So you have multiple cells with lots of pigment that you can pool together to increase their sensitivity. But not so much for, I mean, it's a good idea. Yeah.
They all register all movement on the
Sure. Yes.
I mean something out in the visual field.
Right.
not
Yes.
them.
Right. Yes. So, so in the limit, you could have one tiny cell, just one cell. Given enough time, you can reconstruct. And then the other reason it's not so audacious to think that our fine spatial vision is more of a temporal process than a spatial process. In other words, we integrate over time rather than just simply over space. Other sensory systems are very similar. If I want to sense the texture of my shirt using my finger, I don't touch it, right? I slide across it. And by sliding across it, you build a sense of that texture over time. By sliding the detectors across the image on the retina, you can build a better percept, or better, higher fidelity percept of what's actually landing on the retina. And so it's not so outlandish of an idea. And it's not our idea. Other people have proposed it, but we're the first to show it on this scale, because we have the tools to do it. So just to go back then, I'm going to finish off here, but our adaptive optics tools give us the cellular level access in human eyes, and using them, we can continue to broaden the scope of research that we do, as what I've shown in these slides. So thanks a lot. I'm representing the work for all the tremendous people in my lab. I didn't talk about any clinical work, but that happens at UCSF. But I've got a really outstanding group of students who've been doing the work. And early on, a lot of people doing the technical work that got us to the level where we're at. And then, of course, funding. And without funding, we couldn't do anything, especially with this kind of work, because it's very expensive. So thanks a lot for your attention.